can't. I think this is better. Well, some of the pictures you sent to me, this time only pictures where I see something which should be addressed, like direction of acceleration. Here there is no acceleration as the result. Equations wrong. No acceleration and tension points up. No acceleration. Friction, well, first of all, we normally neglect friction, but if you want to draw a friction, if it's a force, it should not be bent. Acceleration and nothing else. Acceleration points to the right instead of down. Force of gravity points up. Oh, here, just too many arrows. I see gravity, I see acceleration, so, but in general would have been fine. Just don't confuse yourself. Here, first of all, only one arrow plus tension equals mg. When a ball on a string is spinning, tension cannot be equal to mg, never. And here, again, some arrow points up. All other pictures didn't show any things kind of which caught an eye. Now, today, is exactly half of the course, 3 weeks ahead, 3 weeks behind. That's what people call equator. People have weird traditions to celebrate. We don't do anything like that. But since today is a special day, I want to tell you a secret about WebAssign. I told you that WebAssign collects a lot of information. That also tells me, for example, where a person was logging in to the system. The IP address tells us if a person logged in on a VU network. If it's a VU network, probably it's here or lab. Or if a person probably at home, because we don't have here at VU Comcast, So kind of cool and usable. This is what we've talked about last time. Making a turn on a banked track, and we derived that equation, which again, you see, it doesn't involve any friction. So this particular motion doesn't require friction. The optimal speed is related to the angle and the radius. That's it. And this is not the only situation when something like that is happening. For example, if you look closely, rails also banked, and they actually set up so a train, when it makes a turn, should travel at specific speed. And if that doesn't happen, if train travels sometimes too fast, the crash might happen. And a year ago, exactly that situation happened when the train driver was making a turn at the speed which was too fast for that particular turn. And if you're riding a bicycle, you know that when you make a turn, you also don't stay in a vertical position. Why? Well, physics tells you why. When you make a turn, this contact force, which is a combination of friction and normal force, for the optimal speed and radius should point at your center of gravity or center of mass. So if it goes above or below that point, it's not the optimal, and you still feel the motion. Well, we're going to talk about a couple of examples which involve force of static friction. And technically, we know what it is, so I just want to remind you quickly. This is a heavy weight. It says 5 kilograms. 5 kilograms. Even heavier than that weight I was using to crash cans. 5 kilograms. Yep. Well, that's gravity. If we want to see friction, we need to pull on it. And you can see again that if the force is not zero, it doesn't mean it starts moving. Friction prevents it from moving. What do you read here? Let's say 4 newtons is exactly cancelled by friction. If I apply stronger force, 6 newtons, still not moving. So friction, static friction acting on this weight can have any values from, well, 0 to some maximum. Maximum is about 12. So, and between 0 and 12, no matter what force I apply, it's not moving, which means actual value of static friction exactly equal to applied force. Only after kinetic friction starts acting. All right? So now, question. First, let's take a look, and then I will show you the question. Here I have a, disk table, which I can spin, and here I have 2 objects, and right now, they travel together. Why? What force? Is it my finger makes these objects move? No, friction. If I put some oil, make it very, very slippery, in that case, the turntable would be spinning underneath those 2 masses. And the question is, if I start spinning it faster and faster, what do you think will happen? So you saw 2 masses. One is placed closer to the rim, second closer to the center. And of course, we can see what will be happening, all right? So please enter. If you think the one which is close to the rim goes first, enter 1. This is not a tricky question. Just follow your instinct. And now let's check your instincts. This is what we call the first, this is what we call the second. Two critical locations could be used to actually help us to figure out what might be happening. If this is right in the middle, at the center, what's going to happen to it? Nothing. So even if, all right, I don't want to, just be careful. Still. Why? Well, this is a combination of rotational dynamics and properties of friction. Let's quickly discuss. Come on. So, what should you do? You should draw a free body diagram for a single object, right? So please choose. And let's say number 2. Okay, number 1 already has an arrow, so let's say number 1. This arrow represents that force of static friction. Now, we also should have 2 more forces, but those forces kind of really hard to see from a top view because they're perpendicular to the screen. So we can do this. Let's say side view, friction, right? Still points toward the center. We also have normal. We also have gravity. This is static friction. So the value of this friction is supposed to be given by wherever Newton's law makes it to be equal to. And the Newton's law, which relates centripetal acceleration and net force, if we draw our instantaneous axis to the right, says mass times acceleration should be equal to this force of static friction. So if we spin it faster and faster to prevent it from sliding off the table, the force of static friction is supposed to be stronger and stronger. However, the force of static friction has a limit. This limit actually, I think it was, we don't really need that equation, but for static friction maximum, for curious people, the equation for the maximum value of static friction is exactly the same as for kinetic friction. This coefficient, though, might be different from kinetic. That's it. So, but it doesn't matter. As long as the speed reaches certain maximum critical value, the static friction reaches maximum value. That value only provided by the property of the surface. So if we start spinning it faster, friction can't provide sufficient value anymore. Sufficient friction is impossible, and that's why it starts sliding off. Critical value, we can of course calculate it, should be equal to the radius times maximum value of static friction divided by the mass. Another example. Well, this is a model. In the past, to show, close view, I used an additional external camera. Now, I want to try using contemporary technologies. but I'm gonna ask someone to help. So let's see if I can do it. Where is my Skype? This is my Skype. We don't need sound. Come on. See, technology is here. Kill the sound. Now we need to switch camera. My phone is so slow. Okay, whatever. We can do this. Now I need to... How? Could you please just hold it? So, like this. Yeah. Be careful. That's my favorite phone. So now I want to, yeah. And now I want to move away this thing. Well, so you know how the carnival ride works. Yeah. It's you inside, that's you. So if nothing is happening, nothing spinning, you fall down and die, right? So if you spin, you still fall down and die. Because friction is not strong enough to prevent you from sliding down. How can I make a change? How can I add some friction? Well, in this particular experiment, I just make it wet. Friction increases, and in a carnival ride, you would spin it as fast as possible. And now you don't fall. See that green? That's a sponge. Remains attached to the bucket. But if we make it move slower and slower and slower, eventually you fall and die. Thank you. So in this scenario, no matter what's happening, you fall and die. But that's a model, right? So what do I do now? All right. And this is very heavy. That's why I don't want to move it back and forth. I could have asked you. We'll see soon. So, again, all we need to do is just draw a diagram. We have to make a snapshot of an object attached to the wall of a spinning bucket. And again, it's a, well, good practice. Draw a diagram using a top view. If you look from above, that's what you see. Yeah, that's a snapshot. And, well, you can only see one actual force, normal force. And also, there are two forces. Gravity, which always points down, never up. And that force, which prevents us from sliding, friction. And that is static friction. So to see those forces, we can use a side view. Again, that's a snapshot. And the bucket and the center, that's the center of a circle. So this will be the normal force. This will be the force of gravity. And that will be the force of static friction. And again, like in a previous example, we can write the equation. Now it's a normal force which is responsible for centripetal acceleration. M times V squared over R, right? What will be the actual value of the force of static friction? Equal to? What should I write? Is static friction equals what? No, the equation you're referring to says how the maximum value of static friction can be related, maximum can be related to the normal force. We don't really need that equation. To understand what's happening, we have to write the actual value of static friction. What do you think? Actual value of static friction, yes. mg. mg tries to pull it down, and static friction prevents it, and it doesn't fly away. So static friction cancels mg. But again, now we can relate these equations. So the normal force is larger when we spin it fast. See, speed squared. And when the normal force is large, that means this maximum value of static friction is large. That means actual value of static friction has a large limit, so it can cancel gravity. But if we start moving it slower and slower and slower, the normal force becomes smaller and smaller and smaller. That means maximum value of static friction becomes smaller and smaller. And when maximum value is less than gravity, that means actual value also is less than gravity. Actual value, actual friction, cannot prevent you from sliding anymore. And of course, if you want to, we can calculate that critical speed. Critical speed is achieved when actual value of static friction is equal to maximum value of static friction. So, and in that case, we can combine these equations together. So, actual value on one hand is equal to mg. On another hand, for the critical speed, it is equal to maximum. And maximum equal coefficient of static friction times normal. And normal is equal to mv squared over r. That's a critical speed. Mass canceled, and we can calculate the critical speed. Critical speed will be equal to square root g r divided by the coefficient of static friction. Well, this is just, I think, very neat illustration of how physics is being applied. We know that we've talked about roller coasters, and that was an application to a vertical circular motion application to life events, and now similar situations for a horizontal circular motion. That's not a question to answer on a Weberstein. That's a question to say something. What do you think? Two identical masses, exactly same turntable, exactly same objects. They travel together. Which travels longer distance? That's not a tricky question. What do you say? One, of course. We can see. Yeah. This is distance. And what is distance? Distance in the length of the trajectory. First is long, second is short. All right. So we cannot use distances. We cannot, a distance over time is speed. They have different speeds. So the question is, what do they have in common? What physical or other type of variable can be used to describe this type of a motion? What do you think? Well, in this particular case, yes, because objects are identical, but we could use two different objects and still place them on the same turntable. Distance traveled is different, speed is different. What is the same? The angle. The angle. Turns out, to describe rotational motion, the angle is a much more convenient variable to be used. So, first we need to introduce a new unit, which you know very well, a radian. This is an official definition of a radian. If you measure the length of an arc and divide by the radius, the number which we get as the result of this calculation is named the angle measured in radians. 1 radian is the angle which we have when the length of this arc is equal to the radius. In that case, it's like r over r equals 1. That's what 1 radian is. And of course, we know that radians, degrees, and also revolutions, another unit to measure angles, related. 1 whole revolution, like this, 1 whole revolution is equal to 2 pi radians, is equal to 360 degrees. So we can always make a transition from any unit to another unit. But we also can do this. For example, speed divided by time. Speed is distance over time. Now, to describe the motion, we don't use distance, we use angle. So, naturally, we introduce a variable angle over time. And naturally, we call it angular, well, speed or angular velocity. We will talk about direction of rotational variables very soon. So if we take this equation, which is a definition of radians, and divide everything by time, we can get an equation which will relate angular velocity, a new physical quantity, and the distance over time, linear velocity. But for rotational motion, we also use other definitions, like a period. A period, by a definition, is time to make 1 whole revolution, 360 degrees, 2 pi radians. A frequency. A frequency is how many revolutions per second is being done. High frequency, many revolutions per second. Low frequency. So, according to a definition, a period, time divided by number of turns. According to a definition, a frequency is number of turns divided by time. So we can see that frequency and period just inversely proportional. Now, people might use several letters for the same quantity, frequency. In different textbooks and different problems, people use lowercase f, n, or Greek letter. It looks like a V, but it's not V. It's a Greek letter, nu. It's not mu, nu. Still, frequency, 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 number of turns per second, inversely proportional to period. What else can we do? Well, again, on one hand, speed is distance over time. But if an object makes 1 whole revolution, distance traveled is equal to circumference 2 pi r. And time for 1 whole revolution is a period by definition. So this is also how can we relate some variable describing how distance changes and variables describing how angles changes. One over a period, that is a frequency. there are many equations which we can use to describe rotational motion. Angular velocity, angle traveled per second. We should have called it average velocity, but normally for us it's going to be constant. So if we wait one period, in one period, it makes exactly one revolution. However, now we're going to talk about units. A revolution per second is not exactly correct unit for solving problems. It's good unit for everyday life, but if we solve a problem, the correct unit for angular speed or angular velocity should be radians per second. That's why we need to know what a radian is. So 2 pi radians divided by 1 period. That will be, again, the same angular frequency. And again, we can rewrite it differently. And if we use this equation, we can relate angular frequency and linear frequency. So there are many, many equations we can use to relate variables. And of course, in the future, we're going to talk about angular acceleration, because if angular frequency changes, we should ask how fast, and change in angular velocity over time is angular acceleration. Now, this is very important, again, to remember this word, a uniform circular motion or uniform rotation, means that speed remains constant. When speed remains constant, we can use all these equations. If speed remains constant, the period is always the same frequency, angular velocity, etc., etc. So please read the problem, because I'm going to ask you a question about it, I think. So this is what is happening. A ball on a string, and, well, we spin it. That's it. And we count how many revolutions it makes, yes? It doesn't matter. You can assume, but it doesn't matter. It makes a circular motion, and we studied extensively this type of a motion. Now we just use the same example to get familiar with angular variables. Question I want you to answer. These are equations. You should pick up an equation you want to use. You should use that equation, calculate. Let's check website. We don't need it anymore. How do I close? Now go back to the problem. In the problem, you see 3 numbers. So you got to pick, do you want to use all of them or not? Which do you use? How do you use? The question, how do you use, means choosing an equation you want to use and then use it, right? So let's see. So far 15 responses. I need more. Did you pick an equation? Which one? No, an equation. Not the answer. So if you browse through the equation sheet, this is angular velocity, this is angular velocity, or this is the same thing. Also, it's here. All other equations are distractors. Now, we could have used this one, but there is another one, which is kind of easier to use, right? Which one? Two pi f. I don't see it on. All right. Still, I wouldn't use that. I would use another one, please. What equation would you use? Again, 2 pi f. But to get f, you to get frequency, you needed to use an additional equation. First, let's see how many people answered. Why wouldn't use an equation which directly relates angle and time? Because according to the definition, angular velocity equals angle over time. 44. Who answered 4? There wasn't. All right. I told you, WebAssign keeps information about everything. So, the equation which directly relates angular velocity, angle, and time is this. That's the definition. The only thing is that the angle is measured in revolutions here. You can write 3 revolutions over 2 seconds, and that already will be the angular frequency. It just the unit of the angular frequency will be weird revolutions per second. We want radians per second. So 1 revolution is equal to how many radians? 2 pi. That's it. 2 and 2 cancels. Radians per second. And all other equations could be used. You have a question? Yeah, I don't understand. You don't understand what part?
The first equation.
Angular velocity, by definition, describes how fast angle changes. So if you know that the angle, like a 60 degree, so it, here, oops. If you know that it takes, let's say, 5 seconds to travel 60 degrees, angular velocity will be 60 over 5. But it will be degrees per second. If you know that it travels, let's say, 2 seconds to make 1 complete revolution. So a revolution is an angle. It's just a weird unit of an angle. But we can transfer revolutions into radians or degrees. 1 revolution is the same as 360 degrees. So 1 revolution 2 seconds means 360 degrees over 2 seconds, 180 degrees per second. Or if we want a radians, We have to convert into radians to pi. So this is a definition of angular velocity. Well, angular velocity is angular speed and direction is coming soon. So this equation is technically no different from this equation. Now, but now actually we can use this equation to answer that question if you want to. Distance traveled, okay. Distance traveled in 1 minute should be equal to, this is speed of this object times 1 minute, 60 seconds. And speed, radius, and angular speed are related. The equation has been mentioned. Again, I don't remember if I said this. This is also a Greek letter, omega. People call it weird W. Yeah. What the difference? W ends point outside and omega inside. So speed will be equal to angular speed times radius. Angular speed has been found, 3 pi. Radius is given, 53 centimeters, which should be converted into meters, times 60. And that will be meters per second. And this calculation is an illustration of why we have to use radians. We cannot use degrees. When we use radians, the result automatically is in meters per second. Otherwise, degrees would remain a part of a unit, would be a degree, and centimeters or meters, and seconds, weird combination. So when we use relationships which connect linear variables like speed and angular variables like angular speed, we have to use international system of units. An international system of units requires using radians. All right. Now we're going to talk about directions, because again, velocity is a vector, including angular velocity. Displacement is a vector, including angular displacement. And this is a definition which means, again, an agreement, right? That's it. Not everybody likes this agreement. People sometimes switch plus positive and negative directions. But we will stick to this agreement. And for us, again, for us, everything which points to the right is positive. Every vector directed to the right has a positive component. Left means negative, up means positive, down means negative. And now, counterclockwise means positive, and clockwise means negative. And one of the reasons for that is that in general, to describe a motion of any object, we should use 3 different coordinates, 3 axes, x, y, and z. X, y, and z-axis in this combination should be represented by the axis which is perpendicular to the screen and which points at you. So if you look at the screen, you need to be careful, otherwise it might poke you in the eye. Remember that. And that means positive. Now, please look at this screen and ask me a question. You should be confused about something. Something needs to be clarified. Bless you, but that's not a question. Again, not a question. I need a question from anyone about anything. preferably from someone from the back. Please ask me a question about this slide. Is everything absolutely clear? Please. Yes?
Why is theta less
Hmm?
So you know the angle in one of the images is less than 0?
The symbols show how we use this definition. If an object travels counterclockwise, so we can take a protractor, we can measure this angle, and we have to say this angular displacement should be positive because according to an agreement, counterclockwise direction set to be positive, that's it. And displacement over time gives velocity. So according to the same definition, when object spins counterclockwise, the angular velocity should be positive. And here, let's say object travels clockwise, so it starts here, we wait a little, it moves over here. This can be measured. We can measure that angle using a protractor, but protractor never gives negative numbers. Protractor gives a magnitude to it. So we have to say that this angular displacement has to be negative, and we have to write a negative number for that. And the displacement over time gives angular velocity, and we have to say angular velocity also is negative. Yes?
What does RHR stand for?
Thank you. Do you know what it is? So why you didn't ask a question? Mr. V, what is RHR? Yes. You know what? Exactly. That, well, I understand why you didn't ask a question, because you knew what it means. This is a standard representation of a very commonly used rule when we talk about rotation. Right hand rule. Well, if we want to apply right hand rule, question, what hand do we use? The right hand. But there are many rules with exactly the same name. Here, the right hand rule helps us just to visualize the motion. So the right hand rule says, if you curl your fingers in the direction of the motion, the thumb shows the direction of that angular vector, and that direction is positive relative to the axis for the counterclockwise motion. But if the motion is clockwise, so you have to curl the fingers like this, and this is hard, that's why it's negative. So clockwise motion tells you that when an object moves clockwise, the vector representing this direction points away from you into the screen, and relative to this axis, z-axis, that will be negative. That's why it's handy. Right-hand rule is handy. And this is, again, just a definition. These are two symbols which people use to represent a vector which points at you and perpendicular to the screen, or away from you and perpendicular to the screen. At you, it's something like this. If you look at the no, like arrow, bow arrow. Yeah. And if it's a real bow arrow, you have feather at the end. That's what you would see if you look at it. Okay, moving on. Now I want you to answer two questions at once. This is the same turntable. We pushed it once. Well, not as strong, yeah. Something like this. It stops after making exactly 3 revolutions. Questions are related. 4 and 5, they are related. Depending on your choice. Here, you should make a correct choice there. So please. Okay, I'm gonna check WebAssign, and I'm gonna get back to this slide. This is, see, that red spot. This is, you look at it. Let's look at it. Work. The magic word is not please with this device. It's do. Do your job. This is the red spot. And we make it move. Well, not exactly 3 revolutions, but it doesn't matter. Okay. That's what was happening. And so, is it a uniform circular motion? What do you think? Why? Close but not exactly correct answer. Why? A uniform, that word means what remains constant? Speed. And speed clearly changes. It slows down. Speed was not 0 and then 0. That's all we need to know. It changed. So it's not a uniform circular motion because speed changes. Now, about angular acceleration. So it was originally it was moving. Here I see it counterclockwise. Counterclockwise. Counterclockwise means from here to here, for example. So theta, the angle, positive or negative? Positive. Why? We agreed on that. That's it, nothing else. Counterclockwise means, all right, what about angular velocity? Positive or negative? Positive angular velocity is equal to this. Theta is positive, omega is positive. Theta is negative, omega is negative. Okay. What about angular acceleration? What do you think? Why? Exactly. We have to apply exactly the same logic we've used to relate velocity and acceleration before. First of all, we need a letter. And angular acceleration usually is alpha or epsilon. I don't know why. And again, slowing down means acceleration is opposite to velocity. In this situation, it means acceleration should be negative. Exactly the same reasoning as before. Well, so not a uniform, and alpha is negative, and yep, the answer. This is what we need to imprint in the memory. Speeding up means angular velocity and angular acceleration parallel to each other. Slowing down means opposite or anti-parallel. Now let's calculate something. Well, it says everything. Let's calculate something. For example, what can we calculate? So we had initial velocity. It was equal to 5 radians per second. And we know final 0. Now, 3 revolutions. What physical quantity is that? What is the name? And what letter should we use for that? Revolutions, or also known as degrees, or also known as radians. So, angle, theta. 3 revolutions. But we need to convert into radians immediately. 2 pi radians, 3 times 2 pi radians. Now, that new variable we talked about, changing angular velocity over time, it should be assumed constant, because that's the easiest assumption to make. And now, as long as we said acceleration is constant, we have a list of equations we've used before for the motion with constant acceleration. But that motion was linear. This is a circular or rotational motion with constant acceleration. But as we saw, the equations are related by a simple operation. We take any linear equation, divide by radius, and get an equation for angular variables. So here, we had an equation, v final squared equals v initial squared plus 2 times a times distance. The equation which had no name. Here I want to use the same equation. I just want to divide everything by actual radius squared. And this gives me the equation which uses angular variables. Initial squared. Now, this is exactly angular acceleration. This is exactly angular displacement. And now all we need to do is just use the numbers. 0 equals 5. That's why I needed radians, because I have to use international system of units. Plus 2 times. Now we need to multiply 2 numbers. And one of these numbers is positive, which the motion was counterclockwise, the angle is positive. But another number is negative. Alpha from this equation is equal to, this is the magnitude of the angular acceleration, is equal to, 5 squared divided by 12 pi, wherever it is. Please tell me. 6.5? You're lying. 5 times 525 divided by 12. That's 2.08 divided by pi, which is 3.14. 0.663. And that's supposed to be radians per second squared. Yes?
I'm confused where you got the equation for angular acceleration.
Which one? This one?
Yeah, 5 squared over 12 pi.
Well, check my math. This is what I did. I keep 5.
Oh, you solved for...
I solved, yeah. 2 times 6, 12. 12 pi. What can we do now? Well, now alpha is equal to this over this. So time will be equal to, this is the magnitude, omega. Time will be equal to 5 minus 0 over 0.66. .6. So the equation I used now was this equation, which is an official definition of angular acceleration, change in angular velocity over time. I just solved it for time because I know initial velocity, final velocity, and now I know acceleration. It's exactly the same type of thinking we used before. It's just now we add a word to everything. We say angular displacement, angular velocity, angular acceleration, but it doesn't change a thing. So these are equations kind of what we used to use, and now what we can use for motion with constant angular acceleration. We just need to, again, keep in mind that acceleration can be negative or positive, depending on, again, what is happening. Same as velocity, same as displacement. Any questions, please? Yes?
How did you get the rotation?
This is an equation which we use as a definition of angular displacement in radians. And the rest is just divide by r by r squared. Distance traveled over radian, over radius gives the angle in radians. Yes? It was negative. I took it into account here when I wrote this minus. So alpha here represents the magnitude of it. But you're right. Technically, I could have write just alpha and solve, and that would give me a negative number. And the negative number would tell me the direction. So if we know the direction, we can use that fact. If we're not sure, we can just solve and see what's going to happen. All right. So solved. And now we're going to start a new topic. Well, and we're going to start from a difference between a circular motion and rotational motion. A circular motion, when something small like a ball moves in a circle. However, if we have a large solid object like this turntable, all individual parts of this turntable make circular motion. This spot, this. If I make this table move about its axis, so they all make circular motion. So basically, a rotational motion is a combination of many individual circular motions. And what's good about rotational motion, all parts of this turntable, even if they travel different distances and may have different speeds, but they all have make the same angular displacement. They all have the same angular velocity, angular acceleration. That's why those variables, angular variables, are very important. Well, so that's a definition. Translational motion. What's the difference between translational and rotational? Rotational, translational. And of course, in general, could have been a combination. That's going to happen probably in a day or two. So, rotational, translational, and that we call rolling. So we've learned everything about translational motion. For translational motion, we just need to look at one point, center of mass, and all other points move exactly the same way. For rotational motion, we need to look at any point, usually at the rim, how it moves about the center. And when we learn everything about rotational motion, we will be able to combine and talk about rolling. Okay, it's not for the web assignment, it's just for you. What do you think? Why do we open the door usually by applying a force like this? We don't do it like that. What do you think? There are many possible answers for that. For example, my parents told me so. What do you think?
It won't move if you push it closer.
Well, actually, it might move, but it's going to be much harder. And who likes hard work? Do you like hard work? Not really, yeah. So this type of a motion is a rotational motion. When we open the door, when we close the door makes rotational motion. And it's not the only rotational motion which is important in our life. So we need to investigate different situations. Yeah. Same force, but the effect is different. It depends, and we know the feeling. So now we need to make a transition from the feeling to data. And to do that, we need experiments. We know this guy is very heavy. So to make it move, we need to apply a force. And that force has been measured. That force to make it move is about well, let's say 16 newtons. So if I make it move, that means the force acting on this guy reached 16 newtons. It doesn't matter how I make it. We know it only starts moving at 16 newtons. All right, let's see what's going to happen if I pull on this string. It's not 16. But here, when it starts moving, it was 16. What's going to happen if I pull on, let's say, this string? Do you expect to be again, I know that when it starts moving, we have 16 newtons here. But force I have to apply to make 16 here is not 16, it's actually like 34. But it wasn't 34 here. And this motion, which I want to make, is a rotational motion. The rotational motion about this axis. It's like a door. So, first conclusion. When we talk about rotational motion, the force itself might not matter when we talk about rotational motion. Come on. It is not just the force what matters. Okay. Let's see. 14. About 20. 44. One more time. To keep it horizontal, about 20. What if I change the angle? 26, 25. The force of gravity acting on this rod is the same for all my experiments. But the force I needed to apply to this rod to keep it horizontal depends on how do I apply it. Depends on where and at which angle. So we need a physical variable which combines force and angle and location. And after many, many experiments like that, people have invented. And one of the first people who used this new variable, torque, was Archimedes. So that's an official definition of the magnitude of the torque. This is a Greek letter again. People call it tau, tau. You can call it wherever you want to. You can call it T. It's weird T. Vertical bars means magnitude. R is a certain distance. It's very important to know the exact definition of it. The exact definition of R is a distance from the axis of rotation of your choice to the point of application of the force. In my experiments, the physical axis of rotation was very clear. It was here or there, the hinge, But the physical axis of rotation doesn't have to be always the mathematical abstract axis of rotation. We can choose it anywhere, like we can choose the zero level anywhere. The nature doesn't care how we look at it, and choosing axis is just our way of looking at the nature. So when we choose the axis of rotation, we have to stick to that choice. Don't change it anymore until we will have to. And relative to our choice of axis of rotation, physical or abstract, relative to that, we should measure distance from a force, a point of application of a force. What is the point of application of a force? It's the point where the force is being applied. And that's R. And the last variable, it's called Y component, but it's a component of the force which is perpendicular to the line which connects the axis of rotation and the point of application of the force. That's what it is. So if my force is at a certain angle, it always has two components. One is parallel, one is perpendicular. The parallel one doesn't rotate. It's like compressing the door instead of making it move. So the component of a force which is parallel to this line, which is aiming at the axis, that component is not responsible for rotational motion. Only that component which is perpendicular is responsible for rotational motion, and that's it. That's how we calculate the magnitude of a torque. What about the direction? What do you think? Right-hand rule, of course. When force exerts a torque which affects the motion in a counterclockwise direction, we call that torque positive. And when torque tries, it doesn't have to move, but at least when torque tries to move an object clockwise, we call that torque negative. That's it. So a torque is a vector. It has two components. It might have two components, positive or negative. Now, well, we just need to do some examples. Here, same door, same force, but we apply it differently. So let's practice. Here, we need to calculate torque 4 times. But each time, we have to calculate it relative to the hinge. Why? Because we are told to do so. That's it. That's all right. I'm going to start from this very slide tomorrow. We're going to do more examples on torque, of course. But technically, already now, you can solve several new problems on the last part of a homework. All you have to apply is the definition. Good morning. Yeah. There's more stuff to